Hello everyone, so in this video I want to show you how to identify the molecule shapes or VSEPR by using the virtual experiment in PhET simulation. So let me introduce myself. My name is Christopher from Ten Science 1 and I'm from Tunas Bangsa Christian School Gading Serpong. Okay, so before we start, we should know what is VSEPR. VSEPR stands for valence shell electron pair repulsion. So VSEPR is related to the bond angles or the molecule geometry and the last one electron geometry. So the this picture is the scientist who involved for the history of the VSEPR. Okay, short history. In 1939, the idea of correlation between molecular geometry and number of valence electron pairs are originally proposed by Ryotaro Uchida. Then, in 1940, that idea was independently presented in the Beckerian lecture by Neville Sidgwick and Herbert Powell of the University of Oxford. Then, in 1957, Ronald Gillespie and Ronald Sidney Holm of University College London refined this concept into a more detailed theory capable of choosing between various alternative geometries. Okay, so this is the link of the PhET simulation. Okay, so this is the preview of the PhET simulation of the molecule shapes or VSEPR. So we press the play button. Okay, so the molecule shapes has the two sections. The first one is model and the second is the real molecule. So first we click the model one. Okay, so to identify the molecule, okay, we click the tick box of the electron geometry and the molecule geometry. So both names are linear for this molecule. Okay, because this straight line, so straight line is linear and supposed to be the angle bond angle is 180. Yeah, right. Okay, next, uh, if I add one bonding and one bond, okay, so the name of the molecule geometry and electron geometry are trigonal planar. Okay, so the bond angle is 120. Okay, what if I change the single bond into a double bond? Okay, so the name is the same and the angle is still the same too. Okay, what if I change into a lone pair? So the name of the electron geometry is still same, trigonal planar, but the molecular geometry is bent because if you imagine without looking the lone pairs, it's like bent the molecule. Okay, so the angles is 120. Different if I, yeah, lose the lone pair is 180 and if we use the lone pair is 120. Okay, next if the bonding is become 4 and okay, so the name of the molecule geometry and electron geometry is tetrahedral. So all of the sides have the bond angle is 109.5. Okay, so if we change one single bond into lone pair, okay, so the name of electron geometry is still the same, but the molecule geometry name is trigonal pyramidal. So if we imagine without looking at the lone pair, it's like a pyramid. Okay, like okay, so like this, 1 2 3, okay, 5 it's like a pyramid, trigonal pyramid. Okay, clear. Okay, what about if I change again the single bond into lone pair? Okay, so still the same, the name of the electron geometry, but the molecular geometry name is bent. Okay, so next, if we put become 5 single bond or 5 bond. Okay, so the name is both names of I mean the molecular geometry and the electron geometry are trigonal bipyramidal. Okay, so we see in this side the bond angle is 120, but this side is 90 degree. Okay, if we change one single bond into lone pairs, so the name of electron geometry is still the same, but the molecular geometry name is seesaw. So we see like this, yeah, it's like a seesaw. Okay, if we change again one single bond into lone pair, so the name of the molecular geometry is T-shape because the shape is like letter T if without the lone pairs, but the electron geometry is still the same, trigonal pyramidal. Okay, so next, if we put again and becomes 6 single bond or 6 bond, the name of the molecular geometry and electron geometry is octahedral. Okay, so every side has the angle is 90 degrees. So if we change one single bond into one lone pairs, okay, the electron geometry is the same, but the molecular geometry is square pyramidal. So if we imagine, we draw, okay, so 1 2 3 4, sorry, yeah, like this more or less, yeah, it's like a square pyramid. Okay, the angle is still same, 90 degree. If we change again one single bond into one lone pairs, so the name of the electron geometry is still same, but the molecular geometry becomes square planar. You see 1 2 3 4, it's like a shape. Okay, we change again one, okay, become, okay, so the molecular geometry becomes, the name is T-shape, but the electron geometry still the same, the name. Okay, how about if I change like add one single bond into double bond? Okay, the name is still the same. Okay, so you may use this bonding to make what molecule or lone pairs and identify the electron geometry or molecule geometry and the bond angles. Okay, so next is the real molecule. Okay, so we see the model first. So based on the section before, the model is supposed to be the molecule geometry is bent and the electron geometry is 1 2 3 4 tetrahedral besides the center, yeah. Okay, so we see, yeah, right, H2O. So we write the fluid structure or the covalent first maybe. Okay, so O H H, yeah. So H has around only one electrons, and oxygen has six electrons, so share with like covalent bond. So one, two, okay, three, four, five, six, same like this model. Uh, it has two lone pairs. Okay, so the Lewis structure is H1O. H. Okay, so we make one line because it has one pairs. Okay, one pair. Okay, clear. Okay, so we see the real one. Okay, we see the model first. Wait, the bond angle is 109.5, but the real model is 104.5 because the lone pairs decrease the bond angles. Okay, so how about carbon dioxide? So in carbon dioxide, the name of the molecular geometry and electron geometry is linear. So the angle is 180. So we see the real one is also 180 degrees because there are no lone pairs. So how about sulfur dioxide? Okay, so the model, this is the model. So the molecular geometry name is band and the electron geometry is trigonal planar. Okay, so we see the angle is 120 degrees and the real one is 190 degrees because of the lone pairs that decrease the bond angles. So how about xenon difluoride? So in the model, we see the name of the electron geometry is trigonal bipyramidal and the molecular geometry is linear, yeah, because it's straight line. Okay, so this one 380, but the real one is also 180. This is an exception for this one. Okay, so how about boron trifluoride? Okay, so the name of the electron geometry and molecular geometry is trigonal planar, and the bond angle is 120, and we see the real one is also the same because there are no lone pairs. So how about chlorine trifluoride? Okay, we see the model first. Okay, the name of the molecular geometry is T-shape and the electron geometry is trigonal bipyramidal. So the bond angles is 90 degrees, and we see the real one is 87.5 degrees because of the lone pairs that decrease the bond angles. Okay, so you may choose the another one if you want to try. Okay, okay, so this the two section of the PhET simulation. Okay, that's all for the PhET simulation. Thank you for watching.